thing that, okay, you have the talk on this interesting and complex subject of the absorption system in Novae ejecta. Um, what is not easy to understand is how the velocity of the absorption system can increase in a single ejecta. It is relatively easy to understand how multiple ejections or ejecta followed by a wind can produce such evolution toward higher velocities. Clearly, in a single ejecta, which it will imply the optical depth, the recombination wave, and so on. This is much more difficult to understand. I hope that after your talk, we shall be able to understand the evolution of the absorption systems studied largely during the last century by Cecilia Payne-Gaspochin and so we have
McLaughlin.
all McLaughlin. Yes, thank you. So
No,
go
all right,
on. Thanks.
you've you put a challenge. So let's go for it. First, the important thing to keep in mind in what I'll be talking about is that there's one thing that makes absorption or a deficit of light at a specific wavelength an especially important aspect of the spectrum. Emission lines attract everybody's attention because,
Steve,
yeah,
sorry to interrupt. You're coming through garbled for me. I don't know if that's the case for anyone else.
okay, let's try it. Is this any better?
Say something again.
Is this any better?
At the
Yes.
moment, for me, yes.
Okay, then I'll have to do a more in your face to the screen, I guess. Okay, so
sound okay here.
it's just since this is for the record and being recorded, I'll make an insult to Italian Telecom that I've been having, and I'm sure others have had, problems with velocity of the internet and other problems related to communication. So if at any point I get garbled, make sure that you let me know, okay? And thanks. So, okay, to go back, when you take a typical spectrum and you want to get somebody excited about check, you always go for the freaks, and the freaks always wind up having emission lines. So since when you do an emission line study, you don't have to see a continuum because you're just seeing whatever it is that's above a certain level. There tends to be a concentration on the lines in emission and the structure of those lines, and that's what we've talked about in a lot of these objects. But there's one thing to keep in mind. When you see a dark line, I know this is going to sound silly, but it's easy to forget this. The presence of an absence of radiation, and I'm not going to call it an absorption line for the moment. When you have at a fixed wavelength a line with a deficit of emission relative to a background, that has to be in front of the background source. Okay? That is, you actually have geometric information regardless of anything else. You may not know where it is relative to the source against which you're seeing this deficit, but you know that it's intercepting another light source and that it is along the line of sight. Now, this is not a trivial point because when you're dealing with flows or outflows, and anytime you're dealing with unresolved sources, it's essential that you have some information about the line forming region other than simply the emission lines. As we discussed at other times, when you finally have a source in emission, if you see forbidden lines, for example, it's transparent. Every point is going to map into some velocity, but you have no idea what the origins of that mapping is. So you could have something that lies in front of something else and is moving toward you, or you could have a source which is collapsing toward a center where one side is moving away from you and one side toward you, but it's in the opposite sense to an outflow. If you see if you see only emission and the only thing you have is, say, a snapshot, so a one-shot observation, you can't tell. The other is that the emission structure depends on being able to excite. That is, you're always seeing something coming from a higher energy level, which means you're not seeing something from the ground state if you've got a scattering event. So here, let's try it this way. Let me try a whiteboard. Okay, so
That's okay. We see the blackboard.
you do see it. Okay, so presumably I just, okay, start drawing. Okay,
Please, guys, do not move your mouse on
okay,
the
great.
blackboard.
So let's say you
This
are,
is only for Steve.
boy, that's exclusive. So if you're seeing an emission line, remember that the only way you're going to see it is if it's coming from an excited state. So if this energy is greater than zero, then among other things, either it's in recombination or it's in scattering, or worst of all, it depends on collisions, in which case the thing that's going to matter is that you're seeing this as some multiple of the temperature. Now, what I mean by that is that you can have, an upward transition that gives an inelastic collision that gives some energy to the atom, puts it in an excited state. Now, that will, after a finite time, decay, or if another collision occurs, then you're not going to see any line at all. And the collision balanced case is what one calls local thermodynamic equilibrium. It's the thing that we were talking about from the very beginning. But if you've got something from an excited state because of recombination, let's say you have an ion like oxygen +3 that recombines with an electron, so it goes into an ensemble of states and just cascades downward from some upper level down to a lower level, emitting on each one of these without any re-excitation. This is just going to give you an ensemble of emission lines. But it's still going to depend sensitively on the temperature because you're going to have some excitation that originally got you here above an ionization limit. And then from that, in a very temperature sensitive cross-section for the capture, you embed the temperature as a parameter. And the higher the temperature, obviously, the more unlikely the recombination is going to be because because of the energy of the impacting electron. But there's another possibility that if you have, let's just say, a two-level atom, and you have everything in the ground state, and you shine light into it, then you're going to get, if you have the right energy, you're going to get an excitation to some other energy level. Okay? A straight, real, honest-to-God absorption. Now, the most important thing here, and I'll keep emphasizing this in our discussion today, so I hope it won't get excessive. You start from a lower energy level. So it's not, if it's from the ground state, as some of the cases we'll deal with are, it's not temperature dependent. You get a direct measure of the number of absorbers along the line of sight because you're starting from E equals 0. Even if collisions were to bring these two states into balance, and then you had an absorption from, say, this first level. So this is level 1, this is level 0, this is level something. This upward transition would still have an energy dependence that would be less than if you had collisions and then a de-excitation by radiation. So the importance of seeing absorption lines is several-fold. First, they're energetically simple to deal with. That is, all you have to know is the population of the lower energy level, and then the result is directly proportional to the amount of material you have in that lower energy state. The second is, if it's actually from the ground state, then it's proportional only to the abundance, in effect, the abundance of that ion, not just the population of the state, but actually, depending on the conditions in the physical medium, really how much of the garbage you've got along the line of sight in that particular ion, not just the state. So when you see this kind of, well, no, let me back up. There's one other point to make before we go on, and that is that when I drew this, I should have done something like this to indicate that this isn't radiation. That if state 0 and state 1 come into balance because of collisions, then the population of these two states depends only uniquely on the difference in the energy between them and how that compares with the temperature. Okay? And otherwise, the population of these states is fixed. If you've got instead, like here, we'll say a photon comes in and a photon goes out. So what we're really dealing with is, say, something like this, where you have an incoming photon and an outgoing photon that is essentially at the same frequency, but not quite. The thing that's important is it's not going to just be emitted in one specific direction. You're not scattering a billiard ball here. It's going to be emitted in different angles with different probabilities. And so if you're looking, say, here, okay, which is in the line of sight, you're going to see photons coming through, but you're also not going to see some photons. Look, you know this very well. You look at a sunset, since we were just rhapsodizing about this. When you're looking at the sun, the sky gets bright and the sun gets dark. The sun turns red, the sky turns violet or viola or something like that, because you have scattering of the light from the sun. The direct light that's been ruined is scattered from the molecules in the atmosphere and turns it a sort of purple color. While when you're looking directly at the sun, it's reddened and it's fainter. Now, this is a process of pure redirection in the simplest version, that the light from the sun is a pencil beam. That which comes to you has been partly extinguished because it's going through this muck called the atmosphere. Okay? So the light, instead of coming straight through, here is going to scatter in a variety of directions. Now, since the scattering depends on frequency, the light that's coming to you, because this is a continuum, and this is not different than you would get for absorption lines, is going to be redder because the blue is going to be effectively scattered away. That is, the indirect light that is reaching you from here, let's say a cloud somewhere up in the atmosphere, this light is going to be reddened and then bluened, depending on the cross section. So far, okay?
Say yes.
Actually, thumbs work too. Just to make sure that when I ask, please realize that I mean it. I mean, you've suffered through enough by now, so you know that. Now, let's imagine instead that this layer that we've put in isn't in the Earth's atmosphere, it's anywhere. And that somewhere out here in Never Never Land, we have a source. We'll call it a star. Now, the light from that star, in going through something that's intervening, which for the moment I'll call a cloud. In fact, I'll call it an interstellar cloud, is going to scatter. Now, the vast majority of the photons will probably make it through. It's a typical cloud like a cirrus or a non-self-gravitating, not strongly condensed molecular cloud or hydrogen cloud. So most of the light in making it through, and I'm not talking here about reddening. This isn't the same thing as putting dust in the way. This is atomic or molecular. The light that's going to be affected will be absorbed in the ground state and then re-emitted in some other direction. This is critical for understanding everything that Francois had suggested I talk about. It's very important that you keep in mind that the absorption takes place from and in the direction of the source, but the re-emission process depends on the details of the state from which the electron is exiting. So if you've got a dipole transition, the radiation pattern from that is forward and backward. Okay? So if you're at a slightly skewed position, even if you're dead center, not everything is going to be forward scattered. If that were the case, you'd be looking at the source itself, which is just a vacuum. As soon as you put anything in the way that can electromagnetically sense the presence of that signal, the re-emission process, even if it's isotropic, will still reduce the number of photons in the forward direction. Once you know that, you realize that all you need to know is the cross-section. Then, from how much light has been removed, you can tell directly how much material was in the way. Now, let me go to an example of that. So it's going to take finding the appropriate screen here. So let's do one of the unfortunate circumstances of life on Earth is that we can't see the ultraviolet. I realize how silly that probably sounds, but as somebody who works on issues of the interstellar medium, for example, not being able to see the UV is a tremendous impediment to research because the ultraviolet is where most of the resonance transitions are of most elements. It's hardly surprising because the ionization potential, that is what's required to actually excite or remove electrons, is usually of order a few electron volts. And that means it's going to be in the blue or the ultraviolet, and the heavier the ion, the stronger the charge of the nucleus, the more it's going to be weighted toward the UV. So let me give you an example, which means I'm going to have to do a screen share here. So here.
That's okay. Oh,
And, um, oh boy. So okay, so this is spectrum out of a nova. In this case, it was a spectrum taken in 2015 of nova V 5668 Sag, nova 2015b. This is a space telescope, an HST observation taken, in this case, with STIS, which is in a shell spectrum. I wanted to show you this because the lines from NOVA are kind of obvious, but the ones that I want you to concentrate on are these things that look like they're mistakes. That is, to zoom in on this, these happen to be lines from the interstellar medium between us and the nova. And I'm bringing these up because I want you to see what atomic lines look like in a medium that is so low density that there's no broadening, where individual structures can be dynamically isolated from each other, and where we have something completely from the background source. These are the silicon-2 and sulfur-2 resonance lines in the ISM. There are also some lines of carbon, and this one is a line of silicon. The important thing that I want you to notice is how incredibly sharp these lines are. Their broadening is due only to the relative motion of the individual clouds or substructures relative to the nova along the line of sight. These lines will always be there. That is, if you take multiple spectra along the sight line, if in following the nova, these lines won't change. Now, this is an important feature of absorption. In this case, it is pure scattering. The collision times that we're talking about for this medium are of order 10 to the 5 to 10 to the 6 years between individual events. The only reason you're seeing the lines at all is because there happens to be light, all of this light, incident on the cloud that we are looking through. And so the atoms, in this case, or the molecules in the cloud, are removing photons from the line of sight. Now, although I don't have a good example of it on photo immediately at hand, I can remind you that if you look at a searchlight, like the kind that are used in advertising, you'll notice that you can see the searchlight out to some distance away from its source, and then you see nothing. Okay, what I mean by that is you can imagine that you have, oh, it's the same thing with a flashlight, but use a very highly collimated beam. As it propagates through the medium, you see it, right? Like the lightsabers in Star Wars. But at some point, you don't see the beam. Okay? It appears to stop somewhere in the sky. Now, if it happens to sweep over a cloud, it may happen that you suddenly see the cloud illuminated. But otherwise, if there's no cloud, there's a point beyond which you can't see the light. Okay? The reason is simple. The light that you're seeing is being scattered out of the line of sight, or sorry, into your line of sight. It's being scattered out of the beam. So if you want to know the optical depth, in other words, how much crap there is in the atmosphere, look at the beam and see how far it gets. And the point at which you lose the visibility of the beam is of order optical depth unity. So there's a perfect example that if you stood beyond that point and you looked actually toward the beam, you wouldn't see it. Okay? Because all of that light, in principle, would have been scattered out of your line of sight. Here, if you look carefully, you'll realize that you're not seeing anything, that this line, this actually is the resonance line of sulfur-2. There's so much, the line is intrinsically so strong, and there is so much of this ion along the line of sight that the brightness at the center of the line is as close to zero as the spectrograph allows you to measure. This is a very optically thick line. But you will notice that on either side of the line, you're seeing light. So this is something that's very opaque in that species. And if you look right next to it, you'll see that there's another line, which here, so this line, and this line are actually three different clouds along the line of sight. They're not going to move. So you could look at this nova now, years afterward, or you could have looked at it a matter of minutes after the first spectrum. You would see exactly the same absorption pattern. Now, in this case, there's another advantage. Because these are in front of the nova, you know that whatever dynamic you see, whatever velocity these show, has nothing to do with the nova itself. And so this gives you a frame of reference because the absorption here is actually from clouds that are orbiting within the galaxy. Now, there's also some random motion that the cloud has. In other words, the flow. When I say cloud, please don't think of this as something warm and fuzzy and like a little bunny that's bouncing around in the interstellar medium. It's just a condensed region within a very large flow, exactly like a cloud in the sky. It's not that the cloud is moving relative to the air. It's that it's being advected with the air as a condensed region. And the same thing here, as the material in the interstellar medium is pushed around by interactions with winds and shocks and the overall orbital dynamics around the center of the galaxy, you'll see that reflected in the lines that are from the medium between you and the source. So here there are at least 3 clouds. You see, the important thing is you see that they have, in fact, the same atomic characteristic, but different depths and different velocities. Now, comparing this region with, say, here, the lines, these 2 lines are from carbon, specifically ionized carbon. And these lines are from neutral oxygen. And the thing that I want you to notice from this spectrum, because this is going to be important in understanding more dynamical media, is that the velocities that you get for these are the same. This is a doublet, 1334, 1335. This is a doublet for the neutral oxygen at 1302 and 1304. There's also a silicon line, which is barely visible here, and also some neutral carbon lines and a bunch of others that show up in different parts of the spectrum. But concentrate on these at here. These 2 lines are from an ionized species at the same place in the interstellar medium, judging by their velocity along the line of sight as the oxygen. And yet the profiles are not quite the same. Now, neutral oxygen remains neutral up to a little bit higher energy than hydrogen. Carbon, on the other hand, ionizes at a couple of electron volts less. That means that exposed to the same medium, the oxygen can be neutral while the carbon is ionized from the same medium. It doesn't mean that if the carbon is ionized, so will every other element in the cloud. That iron ionizes at 7 volts, carbon at 11, oxygen at a little over almost 14, nitrogen at above 14. Each one of those will show a different ionization stage depending on the conditions in the medium. The conditions in the medium will produce the same absorbers. Okay? And this will be stationary in that when you look at these, you'll see that these lines are the ones that don't change as you're observing. Now, this happens to be important because you see that these absorbers are seen against a whacking great emission line, which is the line from the nova. And over time, that line disappeared, but the absorption remained. So what this effectively does is, even if we were uncertain about the wavelength correction or the identification of the species, we would know precisely what we were looking at because these have fixed wavelengths. the extension of what I've just said goes far beyond the galaxy. And it's important that I bring this up because I think it's a very beautiful example of applying spectroscopy and the same reasoning that you're so familiar with. Instead of
Steve?
saying, yes,
A question, would these two lines you're referring to change with temperature or density of the medium?
they will change in their wavelength, but they will change in the strength. For example, the 1334, this bugger, is the stronger of the two carbon lines. And you can see that also here. That you see that this line is completely saturated. Again, there's no light here. This is really zero. And yet this line, which is from a slightly excited state, and by excited, I mean a temperature difference of 100 degrees. This one isn't as strong as this one. Same velocity. Okay? So this is the answer to your question. Yes, it depends on temperature. If you lower the temperature, this line will get stronger. As the temperature goes up, these two become more nearly equal. If the medium is collisionally dominated, then these two lines can be nearly equal. And if it's really saturated, then this line, if it actually saturates, will be as completely optically thick as this one. Yes, they will change depending on the temperature if they happen to come from slightly different energy states. Now, the oxygen line, on the other hand, are two lines from the same ground state. Calcium are two lines from the same ground state. Calcium, two lines in the optical. And the ones that I'm going to talk about later, the sodium lines, are also from a common ground state. So there, the only thing that changes depends on the amount of material, not on the temperature. See, okay, let me put it this way. I'm not convinced that that's the best way of explaining this. I have to somehow find okay, so to go to the whiteboard again. Okay, so you're I hope now you're seeing my product here. So now the carbon lines actually come from a state that looks like this. This is the 1335. And this one, yeah, is the 34. So the difference between these actually produces a line we can see in the interstellar medium at 153 microns, which is equivalent to a temperature of a few hundred degrees. It's actually a forbidden line, which is why the populations of these two states are kind of fixed relative to each other, because, as I said here, when you can have, or rather here, that you can get collisional effects that populate these without the loss of photons. That's what happens in carbon too. That the ground state, this splitting, is very, very small. And in anything, for example, like an ordinary interstellar cloud, this comes into collisional equilibrium very quickly. In contrast, the calcium lines look like this. That is, they come from a common ground state. So the carbon depends on temperature, and the calcium does not. Uh, as an aside, there's a very neat application of this, which is to look at the carbon 2 lines toward quasars and realize that as you look farther back in the history of the universe, the temperature of the radiation of the cosmic background changes. So when you're at like a gigayear back, the temperature should be something like, instead of 2.7 degrees, it's more like 6 degrees. And that small difference changes those lines. So you can use one of the neat papers from early UV observations of the intergalactic medium was finding the temperature of the cosmic background as a function of the expansion of the universe, and using actually these carbon lines as the model. I hope that long answer wasn't too much. So now to go back to sharing, okay, so we the next important step is this application I just wanted to mention. You all know that quasars are very bright and very far away. We've established that they're actually active galaxies seen in an earlier stage of the universe, and that quasars are at the upper end of the luminosity of these things, and so they can be seen much farther back in cosmic time. And you also know, I'm sure, that the expansion of the universe is something, I'm sorry, that there's a shift, which is related directly to the look back time. That the farther something is, the greater the redshift of its spectrum. And let me use this in a way that doesn't require the phrase, the expansion of the universe. The redshift, this change in the wavelength of the lines, is monotonic. That is, the farther away something is, the greater its redshift, period. That also happens to be a look back time. The farther something is, the earlier in time we're seeing it, because of the finite age of the universe, of this stage anyway. So when you look at a quasar and you get the redshift of the lines, this gives you an indication of its distance. Exactly how you then correlate the distance with time, with look back time, and with physical distance depends on a cosmological model. But the one thing you know that you have as a singular advantage that you do not have when looking at, say, interstellar clouds, is if you see an absorption feature in a quasar at a velocity, in other words, a redshift, different from the quasar, just like the nova spectrum I was showing you, then you know that what is producing that absorption line is lying between you and the quasar. The other advantage, which we don't have in the ISM, is that if you've got a few, say, quasars or galaxies, and you look at their spectra and see these absorption features, which, remember, is scattering. Okay, it's like the interstellar medium. Then if several different quasars at different redshifts show the same dark lines at the same redshift, that means that although you have, make sure that Okay, so you can see my hands here, right? So if you have, say, these two quasars at different distances, and then both of them here show the same absorption feature, you know that they are being seen through something that on a spatial scale related to the redshift is at a fixed distance between you and the quasars. In other words, it could be looking through a screen. If you see multiple absorptions, every one of those absorption features maps to a cosmic distance from you. So in effect, looking at how the different redshifts appear in the absorption spectrum maps out where these absorbers are along the line of sight. The argument that's been used now for understanding this is that the absorbers are actually the interstellar medium of other galaxies or clouds related to other galaxies, that they're bound structures, and that those are the ones that have a high enough column that they can produce an absorption that we can then register. So what you're actually looking at are slices in the history of the universe that if two quasars that are a few degrees apart on the sky have different redshifts, they are enormously far from each other in physical distance. They may be hundreds of megaparsecs apart. But if they see along the same line of sight absorbers at the same redshift, that means they're seeing a structure very large that's lying between you and them. Now, having said that, all you have to do is make that time dependent and you're dealing with a nova. It's the same problem.
Can I
So,
briefly interrupt you at that point,
please,
Stephen?
please.
Are you saying that for proper gravitational lensing to be mathematically accurate, you need to be able to look at these changes in the band, in the wavelengths, and make a correction for the distances,
Well,
for the optics?
okay, in a gravitational lens, there are two problems. One is the actual monochromatic lensing action of gravity, that this introduces no net redshift or blue shift. So it would simply be a change in the image structure. And that's the usual thing that you see when looking at any of the images of lenses, say clusters or the more compact lenses that are being found by Euclid and other surveys. The other point, though, is that each one of the paths is physically distinct. So it is, if they were merely going around the point source, or an absolutely pristine, that is gasless, extended source, where you just had the gravitational field to deal with, there would be no problem. But depending on the wavelength and depending on the interstellar medium of the galaxy through which it's passing, the different paths are going to suffer different extinction and different absorption. So if you happen to be sitting in the wrong bin in wavelength, or you don't have the spectrum of the lens, you may not realize that one of the lenses is brighter or fainter, or in your band, visible or invisible, because the damn thing is going through a different optical path. That geometrically and geodynamically, from the point of the lens itself as a gravitational entity, there should be no bias. But you're going through a galaxy or a cluster of galaxies. And so the paths may be different. In that, yes, there is an effect. I hope I've answered the question.
Yes, thank you.
This is a very delicate one because what you'd really like to do, okay, this isn't going to make any difference in the delays. Let me make that clear, that the light traversing a molecular cloud doesn't slow down. The densities are just too damn low for anything like that effect, that it may broaden out. So it's like atmospheric seeing. The lens may be affected by passage through multiple structures which themselves have variable optical depths. It may broaden out, it may become decoherent. There are many effects that we normally ignore because of the bias in the way we find these lenses. But in general, it's not going to be the same thing as in the cosmological case, where you have something at a very specific position that you know. Now, the disadvantage in the galaxy, as everybody knows, is that we live in it. And without Gaia, without the current generation of astrometric missions, our information about where these clouds are located, for instance, would be very limited. The other thing you can do is in the galaxy now, because you have this incredible catalog of literally billions of stellar parallaxes and proper motions, we can choose the targets by taking spectra along some line of sight and comparing those spectra to see something we don't have cosmologically because we don't have as many targets. But you can look at when the lines that you see in one group of stars are either not present in another group or vice versa. So let's say lines from stars within our parsec do not show one of the absorption lines I was just pointing out. And those stars that more than 2 kiloparsecs away from you, if you take their spectrum, oh, they show the line. Then you know where the cloud is. At least you have an upper bound on where it is. And the lower bound. You know that it's somewhere between the first star at 2 kiloparsecs and the last star at less than 2 kiloparsecs that didn't show that feature. That's the logic we're going to use for understanding what happens in Novae winds. It's exactly the same logic. Now, the importance of the cosmological example is that you have what I was emphasizing, a monotonic redshift. If when you look in the galaxy, you're looking along some sight line. So let me go to a wallboard. And okay, so if what I mean by monotonic is simply that if you put two objects here along a line of sight and you have a velocity field such that this has a velocity v0, this has a velocity v1, at v1, and this is greater than v0, and you sit here, then this will produce a spectrum that looks like this. And so this is your rest wavelength. And you know that 0 lies closer to you than 1. Okay? Now, this is the problem. Take the galaxy. Well, sort of take the galaxy. Try again. Okay, now we'll take two points. This tangent point and this tangent point. Okay? And assume that relative to you, this is going around like so. You got to realize that there are points here that will have potentially the same radial velocity as a point here. So if you see a cloud, or sorry, a source here, and you've got a cloud sitting here, cloud sitting here, they have the same radial velocity. On the other hand, this cloud, if you're looking through the galaxy, will clearly have a different velocity than this one. But there's this ambiguity in the location of the absorber when the absorber happens to lie along the line of sight to something that's very far away in the system. So the monotonicity comes from there being a direct relation between the distance and the velocity. In cosmology, if you say this is the redshift and this is the distance from you, the redshift is linearly proportional to the distance, and the proportionality factor is what's called the Hubble constant. And so when you have a linear velocity law, sometimes you'll see in the literature the phrase Hubble flow. All that means is the farther away something is, the faster it appears to be moving. In the cosmology case, the farther it is, the higher redshift. I'm trying, as always, to avoid talking about this kinematically, since it has to do with gravitation. Now, the relevance of this to Novae comes from seeing absorption lines in both spectra. Specifically, here. This is hot off the press. It's on the spectrum from actually yesterday of a new nova in Muscat, Nova Must 2026. The spectra are from Paul Lucas, who has skies in Australia that I'm sure would be the envy of anybody in the Northern Hemisphere. This is one spectrum showing several lines that are quite ordinary for Novae. The top one, this one, is iron 2. The 5169 line is one of my favorites to trace the metal ions because it's one of the few that isn't blended with anything. It just, by sheer chance, it happens to be a member of a triplet, a multiplet that includes 2 lines that are blended with helium and so compromised at low resolution, while this one is not blended with anything. Well, technically it's blended with magnesium 1, but we'll leave that aside. The bottom line is H beta. Now, for those of you who observe emission line stars, and I know some of you have been involved with BE stars, you'll notice that, and probably will have noticed, that every time I talk about the Balmer lines, I never talk about H alpha. The reason is that line is so strong and come from so many different mechanisms that you can't interpret the profile as unambiguously as you can from the higher Balmer series. I'll explain that a little bit better in a few minutes. But you see, the importance here is there are two components on the H beta line. One of them is at like 800 kilometers per second, 700, and the other is at more like 1400. You see they have different widths, and you also see they have different absorption. Now, in this case, I'm going to say again, you got to be careful about not thinking of these as absorption lines. You can call them absorption features if you want, but the reason you're seeing that feature is more likely from scattering than from actual collisional population of the state. Now, the comparison is with the silicon 2 line, which is an excited state line, as is H beta. The H beta line has a lower level of 10.5 volts. Now, if that were collisional, if you were getting a population that was excited by collisions, this would imply temperatures of hundreds of thousands of degrees, which obviously isn't what you're seeing here. The second is that there are multiple features here. Now, take a look then at the silicon line, and something should strike you here. Only one of these lines is present in silicon 2, not both. This other line is silicon 2 is a double at 6347 and 6371. And this is the other silicon 2 line. And it too is a single line. Yet, looking at the sodium, which is a resonance line, these are interstellar. Okay, and the reason I mentioned the interstellar lines before is that these will tell you which are from the nova and which are not. These are from the nova. And you see this doublet has a separation identical to this doublet. So one of these is the D2 line and the other is the D1 line. Now look again, look carefully. One of those, D2, corresponds to one of the features in the Balmer line, the lower velocity. The higher velocity feature, this one, is barely there. Okay? And yet, it's present in silicon 2, and it is not, it's also present in the iron line. So it's there in iron 2, it's there in silicon 2, it's there in the Balmer line, and it's just barely there in the neutral resonance line. Well, that tells you you've got structure, but that the ionization is different in the different components. You've just gotten another dimension from one lousy spectrum, okay? That is, this spectrum is that there's ionization stratification in this medium. It isn't simply that you got a slab that's uniformly moving at 1200 kilometers per second or 1400, and another slab or filament that's uniformly moving at 800 kilometers per second. It's that these two are not the same state of the medium. It's not that they have different abundances. One of the first and original mistakes that was made in the analysis of Novae, now going back to before Cecilia Payne-Kapashkin, going all the way back to the 30s, was thinking that where the line wasn't, neither was the element. So the interpretation here would be, well, there's hydrogen and there's silicon, but there's no sodium. So it's a sodium weak filament. You see the problem? Unless you do the comparison across multiple structures, each individual region will have a different abundance. It's not the abundance of the element, it's the abundance of the ion. Now, this is going to change. We haven't seen this happen yet in Novae, but it will. That in time, as the ejecta become more transparent, some of these lines are just going to disappear. In all likelihood, this inner line will disappear when the entire ejecta are ionized. So when the sodium disappears, the structure on these other lines is going to change. Again, that doesn't mean something dynamical has happened. Let's go through this. When you have a medium that's expanding, anyone will tell you its density is dropping. Now, we imagine, we stop here and go to just hand waving. Nah, I'll do the whiteboard. It's amazing how slow this is. So let me be sort of hand waving here. Now, let's take this. Okay. Now, why is it? I'll show this again. Good. Okay. Now, let's assume here that we have an ultraviolet light source. And the penetration of light, and please forgive the technicality here, but it's really important. We'll assume that this is a source of ultraviolet radiation. Now, the first layer will ionize and consequently remove a part of the ultraviolet. So we'll call this layer, let's say 3, meaning twice ionized. This one we'll call 2. This one we'll call 1. Now, that means that if this is a moving medium such that this part has used these velocities, this has velocity 2, this has velocity 1, this has velocity 0, just for example. And maybe even this has velocity 0. Okay, so these could almost be together. What you're going to see is a feature coming from 2 and 3, and no feature from 1 at this velocity. So when we're looking at the spectrum, if this is, let's say, the spectrum of this one being 2 and 1 on, say, helium-2. Okay, when we're looking at helium-1, we're just going to see this. So far, so good, I hope. That is, this line, the helium-1, is formed only in, say, this outer region. And here I'm plotting in an unusual way. So this is negative and this is positive. Just because I started this with lowest velocity on the left. So what you get if you looked at this at one moment is what I just showed you, that one of the features is going to show up perhaps on more than one ion, and another feature will show up only on one ion and not the other. It's not an abundance effect. It's an abundance of the ion effect. Now, let this expand. The density drops. So does the recombination rate. So instead of having a region which is, say, helium-1, now this region is ionized and it's helium-2. And this region is helium-2. And this region may be helium-3, which actually has no absorption lines. So what's going to happen is this line in helium-1 disappears because helium-1 disappears. So watching over time, you look at which lines come and go. If you have a single ejection, then placing any source inside if you have structures in here, filaments, blobs, whatever, detritus, the kinds of things you see when you look at fireworks and things are blowing off in different directions as fragments. Looking through this, don't looking through this, you're going to get a feature here, each one at potentially a different velocity. Now, let's assume that the whole region ionizes and turns optically thin. Then the emission line may look like this, where each one of these fragments will be one of these. Now imagine, for the hell of it, that you didn't pay the electric bill and the central source turns off for a moment. And you search around to find your credit card so you can get it reignited. But for the moment, it's off. Not being illuminated, this region recombines. And so some of these features that were in emission may now turn back over into absorption. Okay? So this will disappear, and these will suddenly appear in absorption. And then, if you suddenly repaid your bill, so the light turns on, these will turn back over into emission. Now, because the ship is expanding, the stuff that recombines in the inner part has a velocity that's lower. Now, I do not understand why it's doing this. The velocity of the inner component, so if this is V rad, will be initially, so this is now 0, and say this is minus 2,000 kilometers per second. That initially you'll just have this inner shell, and then gradually you'll see these other features showing up. And so you would say, ah, well, look at this. You've got something that's accelerating outward. This is what Francois was mentioning. You would make the mistake, looking at this, thinking that you have multiple ejecta. Instead of saying, no, at this point, this one turns on. This one turns on. It's still visible here. It's still visible here. This is still there. And there's another one here. And then this one stays on, and these others disappear because they're ionized. In other words, you could have a perfectly stationary flow where each feature was like what I was talking about with a quasar. Each feature is fixed, but you're changing the ionization. You interpret that as a change in the velocity because that's what it looks like. And that's why I'm being so emphatic here. You were not, in this case, seeing motion. You were not seeing a new event. You're not seeing an ejection. You're simply seeing something becoming visible or going invisible. It may happen that there is actually a dynamical event. So to guarantee that we actually talk about that, I'll use as an example. If actually, yeah, so if you have, I'll always draw this as a blobby medium. If this is your line of sight and you have something here that explodes. So we'll assume that this is something like like an atomic blast. Then this is a pressure wave that's being outward in a surrounding gas. That gas can be external. It can be the outer part of a wind. It can be the outer part of an ejecta. You don't have to care. All you need to know is that the expansion is due to the pressure being different. This is called a shock. Now, we haven't talked about this in any of the previous discussions, so to make this clear, if this radius is taken as some x, a shock is by definition a discontinuity in pressure. It means that before the passage of literally a wall of pressure, you don't know what's coming. It's expansion faster than the speed of sound, which is, after all, the same thing as a pressure wave. And so the material out here, which originally has a velocity of 0 in our picture, suddenly gets sped up to some velocity 1. What you think you were seeing there is, if you had this as, say, the velocity registered from this column, and this 1, then the contribution from 1 would be this. And so if you saw only one line, low velocity, and then you suddenly saw, say, 2 lines, one of your interpretations would be, you got slammed by a shock. This is one of the standard interpretations that you'll find of light curves for novae, and it's based on the picture that you have multiple ejections, something else that Francois mentioned. A shock wave is compressive. It's a discontinuity in pressure. You know perfect examples of this because if you, yeah, it's actually the best example. If you go into your kitchen and you have here the faucet and spout, and here you have your basin, and you let this run into the basin, you know that what you form is a ring of water which is expanding outward. We'll assume the drain is over here. When that material, when that wall of water slows down, what you get is a rim like this, where you've got this stream of water coming into this wall of water. And then afterward, on this side, the flow will be sort of smooth and it'll be thicker and you'll just barely potentially see the movement. But here, you're suddenly hitting a wall of water. As a show of hands, have any of you ever stared at this in your sink? No, you do. I strongly recommend this as a way of passing time. If you have nothing better to do, you can spend hours at it. What you're seeing is a shock wave. To be quite precise, this is called a bore, B-O-R-E, and it's the result of being incompressible, but it's the same thing. You've slowed the water down to the point where it can come into pressure balance, where here it's moved faster than gravity will communicate to this, that you have a flow that's advancing. It's the same thing here. When you have the passage wave, the material afterward has not only been sped up, but it's been compressed. And if it's compressed, the ionization state changes. So the clue that you've seen an ejection will be that different lines will appear to have different rates of change depending on the ionization state. There's a very clear signature of this, but it's spectroscopic, not photometric. The photometry, the reason people think there are multiple events is when you look at a nova, say on the rise, and you see something that looks like this in the light curve. So V versus time. You are tempted to say, well, there was an ejection event here and it slammed into this and dissipated the energy as a pulse of light. And then there was another, and then there was another. You have, and then got the problem of explaining why you're getting the events happening when they do. Now, I say this for novae, but this is also true for supernovae, and is also true for stellar winds. Ejection events, large, coordinated ejections, not the sort of thing we see on the sun, which we would never be able to actually see directly if we were looking at a solar-type star, the coronal mass ejections. We'd see flares, but we would certainly not see the other dynamical signatures. If we looked at, instead, a pulsating object or one wind, then we may, in fact, see multiple ejection events. We know that asymptotic giant branch stars do this. Planetary nebulae show internal ring-like structures. So we know that things that pulsate, especially if they pulsate with large amplitude, are like waves crashing on a beach. We can get multiple waves arriving, or in the case of the waves crashing in the atmosphere of the star, as the wave propagates out from the piston below, it can eject events. It can eject material. And one of those may show up as one of these. That's true. That's quite well observed. In fact, one of the places this may be seen is in B stars. But it's not quite like we're talking about Novae. Let me go to another screen share. So this is what I was talking about. You've got three different scenarios. One is that you have expelled matter. In other words, you throw off ejecta. In that case, the velocity increases outward. And if you've done it ballistically, then it looks like the flow in the universe. That the farther something is from the center, the faster it's going, or that it's farther away because it was going faster. That's what you see in fireworks. As we've talked about in earlier discussions, if you have a point explosion, not everything is going to be ejected exactly the same velocity. It doesn't work that way in explosions. Okay, so something blows up and you got this range of velocities in the fragments. Obviously, if it happens at a moment in time, the stuff that's going fastest is going to go farthest. And the stuff that's moving slower is going to get less far. And less far means you're going to have a smaller volume and higher density. So, nova ejecta and the ejecta from planetary nebulae have this kind of relation. The fastest stuff is farthest out, but it's essentially velocity and a linear distance relation. Instead, in a wind, you have a driver. This is very important. We've talked about this in an earlier discussion, but I want to reemphasize it. Winds mean that something is blowing constantly and leaving under an accelerated driver. You're going from rest to some velocity above the escape velocity. Okay? To do that requires that you are driving the material outward against gravity. The advantage of ballistic flow is that, at least for a time, there's no effect gravity. You can just ignore it and take the velocities to be essentially constant for each fragment, whatever it was given at the beginning. A wind is a continuous flow. Fragments are not. And as a continuous flow, it must accelerate outward once it's gone supersonic. So there are two things that show up spectroscopically. One is that at the terminus of the wind, where it's now coasting forever, where the driving has gotten it to above the escape velocity, but as it gets farther and farther from the driver, the acceleration becomes progressively smaller, and eventually it just becomes velocity. Okay? You know the inverse of this when you have some nut who jumps out of an airplane and forgets to forgets to pull their parachute, they're still going to reach some maximum velocity in their fall. It'll simply be biologically unpleasant when they decelerate. But the point is they don't accelerate forever because there's, in this case, a negative driver. The driver is gravity. That should cause a continual acceleration. But because the drag depends on velocity, you eventually reach a terminal velocity. Here, it's the other way around. The driver is driving the material outward, which is being progressively impeded by the effect of gravity. Although, eventually, even the driver becomes weakened enough that the material just drifts. Now, that means that you have, at any point in the line profile, a very long path length to look through. So you see an enormous opacity at the maximum velocity and a weaker optical depth at the velocity where this is accelerating. The way you would put it is this is saturated and this is accelerated flow, so it is desaturated. And the line profile that you get out is the classical P Cygni profile, where you see the terminal velocity, because eventually this will, every species, this will eventually drift at constant velocity. Now, in the expelled matter, it's the opposite. There is no terminal velocity. There's only the maximum. Whatever was the fastest impelled fragment, that's it. And so you'll see a line profile which looks kind of like the opposite. It's going to not have this saturated region, and instead it'll gradually go to minimal absorption at high velocity. The third thing is, we'll assume that something hiccups here. Doesn't matter what. Put a blob there. Put an absorber there. Put a shock there. But let's just say put a blob. That blob will be forever at that velocity. As it's expanding, it may disappear because ionization may move it. The density may become too low, but it will always be there. So if you recombine, it's going to come back exactly where it was. Here, any feature, I have to emphasize this, and I hope this is clear, any absorbing or scattering feature that is at a lower velocity than terminal will not remain stationary because it is being driven. This is simply expanding. There is no acceleration here. Here there is. So if you see something that starts out at 800 kilometers per second and the terminal velocity is 2,000 kilometers per second, that will inevitably shift from spectrum to spectrum and will never repeat. This is the key for understanding the difference between these. One of those is a dynamical structure, and the other is a kinematic structure. And expulsion by ejecta is purely kinematic. Now, there's a third, which is kind of the unfortunate merger of both of these, which is otherwise called B star, that you can get disks that have outflows in them. Now, you're actually very well acquainted with something like this. If you take a bowl, fill it with water, and stir it, that you'll get a flow that actually moves outward at the top of the flow and then moves gradually back inward at the bottom. It's a circulation that you set up because of the rotation of the fluid relative to the basin. That part is important for our discussion that anything that puts angular momentum into the flow acts as a driver. In fact, it's leaving the Artemis mission aside and thinking only about much more prosaic uses of space. The launch of a satellite from, let's say, the space station can be done very simply by taking the satellite, keeping it on an extendable arm. If this sounds familiar, it is. This is how satellites were launched from the shuttle. While in orbit, extending that arm away from the station or the space or the shuttle or Artemis. And then once it's far enough away and the Earth is down this way, just release it. Literally, let it go. Don't give it a kick. Don't do anything. What will happen is it will begin to rise on its own because it now has much angular momentum for the orbit that it was in. And so it will gradually move outward to the correct orbit, at which point, when it's far enough away from the station or from the shuttle, it can fire some engine and propel itself farther. The same thing happens with BE stars and with other disks, that there are ways of getting the material to be spun up in the inner part above the value that they should have at that distance for the orbital velocity. And the material will be to move out. And so you'll get the double profile of the disk in emission, but you will get the equivalent of a freaky kind of weak wind in the disk in absorption. Okay? Again, if you look at PE stars with those features, they do not repeat. If this is the case, if you're getting ejection of material, if these are single events that change their velocity over time and trace out the velocity structure of the medium. Now, so okay, now let me just see which window that is. Now, now we're again looking at Novae. I'm just going to put a comparison. This is from a few days ago, and this is the latest spectrum. And so you see that the interstellar lines haven't changed worth a damn. And there have been some very minor changes in the lower velocity feature and some changes in the higher velocity feature. Okay? you notice that the change is such that they're not moving. They're simply appearing or disappearing. Now, what I want to show is one of the problems we're currently working on. So, yeah, do I want this one? Yeah, what the hell? Okay. So this is a very slow nova. The line that I'm showing you is the helium line at 7065. It's neutral helium. I just want to use this as an example. These spectra cover an interval of like 50 days. Always the same line. Different resolutions, by the way, but always the same line. So there's at about 1,300 kilometers per second. That comes and goes. In fact, at first you see only a very narrow emission. I'm not going to bore you with the explanation for every piece of this. Just concentrate on the absorption. So suddenly the absorbing material appears. And then it seems to shift to lower velocity and disappear. And then it comes back at a higher velocity. Or, well, let's go to everybody's favorite line. So H beta. You see, there's absorption. Then it goes to a lower velocity. Then it goes to a broader line. That one, by the way, that shifted badly is because the wavelength solution was wrong. It wasn't that the whole star just suddenly moved left. You notice that you saw a change in the velocity of the line.
Forgive me for interrupting at this point, but couldn't you use the variance of the line to distinguish these things that you're describing?
Yes. Yes. If you mean the variation and not full width half maximum or some statistical parameter, then the answer is yes. If you mean say the second moment, no. That
I guess I was distinguishing the shape of the curve as it speeds up or slows down, the effect on that variance in terms of it being different from a normal distribution.
Yes, absolutely. In fact, one of the things that's interesting about this spectrum is that different parts of the profile change differently. That at the beginning you saw that there was this narrow feature, relatively narrow. Okay, this is 500 kilometers per second. So it was there was a feature here that was sort of marginally resolved. And then it had broad wings and a portion of the absorption appears, except it originally appears here, and there's this narrow component with this broader piece. Let me show you a better example that I think will emphasize precisely what you were just saying. Instead of using hydrogen, let me use iron. This iron too. At first you see nothing. Then There, you see that? Now you see the changes in the line profile, that the velocity of the minimum changes, the whole shape changes, much more to the point. That. There are three different components here. There's something that's narrow at 0, and by narrow here, this is a higher resolution spectrum. So this line in whatever you want as a characterization is only a couple of 100 kilometers per second wide, maybe 100. Then there's this broader wing that you see underlying it that seems to merge into the profile, and that at its base is like 1,000 kilometers. And then there's this thing sitting off to the side at 1,200, or sorry, 1,400, that kind of changes. So it goes from being at like 1,500 to being below 1,000 kilometers per second. So this is like what you mean by changes in the line profile, the variance. It's not that we've lost this feature completely. It's that it's not visible. It's not that it's not there. It's no longer optically thick enough that we can see it. I have to keep emphasizing, because, well, this will, I think, show it even more dramatically. In detail, this is Novae. Each one of these features, iron 2, and all of the Balmer lines. So H alpha, beta, gamma, and delta. You see that even on the hydrogen lines, some features are there on beta, gamma, and delta that you can't see on alpha. The velocity of the minimum is different on alpha than on beta and gamma. Again, that's because you're looking through a flow. And the iron, well, the iron is not at the same velocity as the hydrogen, although it's very close, and the profile looks basically the same. So you would say here that you're looking at an ionized region, the ionized iron, which is covering the same velocity range as you're seeing on the bar lines. Remember, silicon doesn't show this. Eventually, the silicon may, and the iron 2 line may change its profile yet again. Once you've established where these are, you can then trace down the structure of the ejecta. Okay. Now, all of this seems to be just curiosities. I imagine that by this point you're asking yourselves why the hell you're going through this. The only reason to do spectroscopy is that you want something you can put on a wall as a really neat picture. I'll tell you a little joke. In the 1980s, there was a very important satellite that was a joint ESA, British and NASA mission called the International Ultraviolet Explorer. Many of you have heard of this. It was the first true ultraviolet observatory in space. But the only thing about the satellite that well, NASA at the time wanted to publicize the satellites by the kind of neat data they produced. Okay, and everybody knew that that there were satellites that were producing marvelous views of the universe, like some of the X-ray observatories, some of the optical observatories that were imaging devices in one way or another. The problem was this was a spectrograph, and not everybody gets their hots on looking at a shell spectra in the raw. But ESA, in its brilliance, decided that they were going to do a calendar of IUE spectra. And what they did was literally show the raw spectra, of which one of them was a Wolf-Rayet A star, one of them was an H2 region, and this was, I think, the most obscure and ignored publicity that the space agencies ever produced in their 60-plus year history. I'm sure probably these are collector's items now because very few of them would not have wound up in the trash bin. So the bottom line is the reason that you do a spectrum is not because it's so beautiful, it's because there's something in it that gives you a window into the origin of that spectrum. This is the way you can, by the fingerprints of the universe, read what the processes are. The only record we have of what happens during those supernova explosions is printed in the spectrum because they're the only way we can get the kinematics, dynamics, and energetics simultaneously. If you're looking at photometry, the only thing you get is the amount of light that reaches you. You can make the band as narrow as you want, but you will never know from where that actually is emerging. That was why I was emphasizing the monotonic nature of the velocity fields. As soon as you have time series, whether you have a wind or ejecta or a disk, you can dissect the points of origin of the features in those spectra, and those will link to the physical conditions in the region from which that spectrum is emerging. Since the physical conditions there are contingent on the origin of that site, it tells you about that origin. Specifically, if you're looking at a nova, the structure that you see from the spectrum is what was imposed at the time of the explosion. If you're looking at a supernova, you can even tell how much of the radioactive material, like nickel-56, synthesized during the initial stages of the expansion, when you have nuclear processes happening in the inner ejecta, how much of that has mixed into the outer portion of the ejecta by the way the ionization changes, something you'll never unambiguously determine from looking only at the light curve. In every one of the transient phenomena that we know happen in a very dynamic universe, the dynamics, the energetics, the abundances, and ultimately the drivers are preserved in the spectra and the time series of those spectra. You can get almost all of the information even from unabsolutely flux-calibrated data. But if you can calibrate the fluxes in each one of your spectra, and not just do things relatively, you can even get the energetics that you would otherwise have had from the photometry. The reason photometry was created originally was the only quantitative information you could get about stars at the beginning of the 20th century. Now, think about primitive conditions under which the early observations of novae or supernovae were carried out. The various, like, the selenium photoelectric cell, or eventually the 1p21 photocathode. The photoelectric photometers that were available at the beginning of the 20th century were the only quantitative way you could measure the of any celestial object. Photographic plates were too damn nonlinear. You could use them for velocities, and that's why when you go back to the papers from the 30s and the 20s, McLaughlin and Greenstein and even Rosino back in the 50s and 60s, when looking at all of this body of work that first got incorporated in Payne Cushman's book, now 70 years ago, the Galactic Novae, all that is qualitative because photographic plates depended on how well you developed the damn things. You couldn't trust even the ratios of lines because you couldn't absolutely calibrate the sensitivity of the plates. But you could, by the imposition of a comparison arc, measure the velocities and widths of the lines beautifully. And so the literature before the 1980s is dominated by kinematics. But because you didn't have other bits of information that I've been pushing on you today, you couldn't interpret the kinematics as anything but, say, multiple shells. So when McLaughlin came up with the notion of the principal and the diffuse and the Orion nebular stage, all of that was purely descriptive, saying that the spectra looked like these conditions, but there was no way of absolutely determining that. And so you couldn't model the ejecta. You could only extract the information because the line profiles were inaccessible to you. You couldn't, in fact, tell in a complex case whether you were looking at multiple peaks or peaks and absorbing troughs or multiple absorbing troughs or multiple peaks plus absorbing troughs. You literally couldn't distinguish these under a microscope. So you would have to develop the plate, place it on a scanner, calibrate the scanner. Very few places were capable of doing this, and this is where the literature was already into the 1980s. And to come full circle, this has remained this key. People, all of us who do transients, because our ancestors used stone tools. Okay? In the modern world, we have other means. I've just been walking you through some examples of this. Make use of those. Having digital data, make use of it. Having all the time in the world, make use of it. Being able to follow multiple wavelength regions and doing comparisons between tracers of different ionization and states and elements. Do it. All of these give you that additional information. The example of the absorption lines is most critical because you can then add the one other thing you know about the way that the line is formed. And especially if you have great fortune of seeing an absorption feature go over into an emission feature. Within a profile, that suddenly tells you that the emission peak you're seeing that was associated with an absorption is at a physical location in the medium that you're studying. It doesn't matter whether it's a nova, a stellar wind, a comet. They all behave in this, or a planetary atmosphere. They all behave in the same way. If there's anything I've been trying to emphasize today, it's the key to understanding comes from what we talked about a few weeks ago or a few sessions ago. You think like a photon. You have a source. That source is seen through another medium. Every property of that medium is going to be imprinted on the passage of the spectra of the photons. And so when you have a spectrum at the end, when you've obtained that collective image of the photons, you're seeing the imprint of the medium through which those passed. And that's the bottom line. So, boy, have you put up with a lot today. I hope.
I have a quick one again.
Please.
It comes to mind that a classic model to work with would be jets from, say, something like the Herbig Haro 30 protostar, the work that's been done with JWST and the Alma millimeter wavelength work recently. If you want to distinguish between the ion lines, which seem to follow the jet and obviously affected magnetically, from the cones of the other elements that are present, you should be able to distinguish them on the basis of these velocity variations. It just suddenly struck me that that's a rather nice example.
Oh, definitely. The reason I didn't use that is that they're an emission. We can use the same logic actually for the most extreme jet that I know in the universe, SS433, which is not a protostellar source. It's an accreting black hole that happens to have a jet that's moving at something like a quarter the speed of light and has an opening angle of less than 5 degrees. And you can actually see this as a variable emission and absorption feature because the hole precesses and it's in a binary system. So you see different phases of the jet presenting. What you don't see in general in the Herbig-Aura stars, or specifically in stars like DK Tauri and some of the stars in Orion, is that you don't see the jet processing, but you see some of the signature of that in the larger scale structure. There's also a symbiotic that some of you know, Francois in particular, MWC 560, which is a jet, and that shows the features that I was showing except absorption. So in that case, you actually see material, it's not a recombination effect. You actually see the material physically moving outward, and it's directly connected with ejection events from the binary. Symbiotic stars show this all the time, that they show highly collimated flows. The difference in the protostellar case is that you've got a lot of crap around the source of the jet. So one of the other things, unlike the pristine case that you have in the, say, SS433, or the relatively pristine case in symbiotics, the jet that's emerging from the protostar is going through a cloud. And so in the larger scheme, it's not only expanding, but it's also moving against something. Okay? It's not really expanding. There's a so-called working surface. And that means there is a shock there, which is what people try to use as an analogy with Novae. So you have this expanding front. The material here is not ionized. Here it's ionized, and it's been sped up to not the velocity of the jet, but some fraction of it. So you see the material that's been shocked, and then around it, you'll see other ions that may be affected by the jet, but not swept up into it. That's what you're seeing in the case of, say, the iron 2 versus the oxygen 1. It's not just that the iron is following the magnetic field. This is not an ion or element effect. It's that where you've got this working surface, you've got energy being put into the gas. The gas is being compressed. It's being ionized. And so you'll see the lines from that ion and not from the rest of the material. The stuff around it that's not shocked won't show that line. The stuff that has been shocked will. It's a little bit like saying when you look at the stuff coming out of the spout. In the example I was using, the water that hits the bottom of the sink, you can actually hear, and then the air around it hasn't been moved. Okay, you can take hands and move really, really, really close to the stream, and you won't feel it. But if you put your hand right at the boundary, you'll feel it. Okay? That's what's happening in the protostellar case as well. That there's material of the protostellar disk environment which has been punched through, but which is not entrained. You see the same thing in clouds in the sky when you see a plume coming off, and you have a cloud that looks like literally a rising bubble with a trail behind it. Okay? Around that cloud, the air is stable. Within that cloud, there's a general uplift. But you may be watching that a couple of 100 meters away, a kilometer away, and you'll see the cloud rising, but there'll be no wind where you are. Yet there is in that flow, and if you looked in the water vapor, you'd see that there would be a component of the atmosphere that's not moving, and a component caught up in the cloud that is moving. Of course, that's subsonic. Lots of other reasons why it's just an analogy. That's what's happening with the Detroit stars. Now, the other part of it is that because the material of the jet is ionized, it's dragging the field with it. And that's the reason the field is different. But the ion is because of the dynamics.
Thank you.
It's an absolutely beautiful problem, actually. Perhaps the most remarkable thing of all of astrophysics, at least from the spectroscopic viewpoint, is that so many environments, so many of the flows we see are wildly supersonic in ways we never have access, that we can never access in the laboratory, or in density regimes that we can't even hope to produce on Earth. The most remarkable thing about the spectra is that they give you access to both the dynamics and plasma information that allow you to see regions that you know fill the cosmos, but you can't reproduce in the lab. So if you're a sort of modern day theorist and think that you can use AI to solve all the problems, you build this model and then you make your observations on the model, and you have no grounding in reality unless you look out at the cosmos. And if you don't know what you're looking at, that is, if you don't know the processes that form the spectrum or form the luminous signatures, like the light curve, you're going to foul up.
Thank you, Steve. perhaps you have some short questions with short answers.
Short questions are
On
always
the subject,
guaranteed.
please.
Short answers,
Yeah, even if I know that astrophysics can no,
really
perhaps we can close there and
just one last comment.
with great congratulations to Steve. Yeah, yes.
Just one last comment. Uh, I realize that these discussions have gotten progressively more technical, but you've gotten progressively more technical. And as these things become more familiar, I hope you see that they're not difficult, that it's by building the connections between things and thinking of these as diagnostic tools that the physical processes become primary and all of the rest of these technicalities become details. We have the advantage in astrophysics that doctors don't have. Because we do the same kinds of diagnostics. You know, when you're looking at a CAT scan or a PET scan or an NMR, you're looking at a remote image. Okay? If you know how that image is formed, then you can look at all of the details and not be overwhelmed by them because you can see the connections, knowing the underlying processes. It's the same thing when you're looking at the cosmos, that we're always doing remote sensing. We're doing it with many different tools that give us different kinds of information. And so once you know the physical processes, you can ask how those manifest in these different ways of receiving the information and not get overwhelmed by it. So I hope that's coming across in all of our discussions. And thank you all.
Thank you, Steve.
Have a very good weekend.
Thanks, Steve.
Take care.